Hello, everyone. My name is Eliana Juarez, and I am the team captain of Team 1 from BC Cleveland High School. Our project is combating air pollution by forecasting ground ozone levels.
I'm Sofia Juarez. I'm in 9th grade.
I am Graciela Rodriguez. I am in So before we get into the project itself, we'd like to say a few things. We'd like to thank Mark Peterson, Jenny Juarez, and our teachers Ashley Johnston and Lauren Huey for all they've done for us. So also, just to certify that all original research and code was done by the students. We did not receive help beyond advice on topic choice and the fundamentals of Python and data science. All the graphs were created by student researchers unless otherwise noted. All right, so before we get into the project, I'd like to provide some background information. So first on the problem itself. Air pollution is among the leading causes of premature deaths, causing approximately 4.2 million deaths worldwide each year. Among the causes of death in these cases are lung cancer, heart disease, and respiratory diseases, and one of the harmful pollutants is ozone. Now, to avoid any confusion, allow me to specifically define the problem this project is addressing. You might have heard of ozone before, and if you have, you might be slightly confused. After all, is an ozone good? Doesn't the ozone layer protect the Earth from the sun's ultraviolet rays? Well, yes and no. Ozone located in the stratosphere is good. That is the layer of Earth's atmosphere that is located about 20 kilometers above the Earth. That ozone protects the Earth against the against the ultraviolet radiation from the sun, but that's not what we're talking about. Ground ozone, also known as tropospheric ozone, is ozone that is located in the troposphere, the layer of Earth that is closest to the Earth itself, and it's the layer that humans live in and that experiences weather. This ozone is bad because tropospheric ozone is harmful to both humans and plants. Of course, there were many different pollutants that this project could have chosen to focus on, but ground ozone was selected for several reasons. One thing we took into consideration was that ozone is the main component of photochemical smog. Photochemical smog causes reduced visibility and a variety of health issues. So as the main component of photochemical smog, ozone is a pollutant that has conspicuous immediate effects and therefore is worth tracking. As I mentioned, ozone itself causes many health problems. Health effects of tropospheric ozone can include coughing, lung irritation, throat irritation, wheezing, and trouble breathing, especially when doing physical activities outside. So the people who are affected the most by this are people with lung conditions like asthma, bronchitis, or emphysema, and also older adults and children. Ground ozone also damages plant leaves and can harm agricultural crops. One reason why it is so important to be able to predict when ozone levels will be highest is so that high-risk people can know to stay indoors, and so that people in general will know to limit their use of ozone-emitting activities. Another factor was ozone's status as a secondary pollutant. Secondary pollutants are not directly emitted. Instead, they are the product of a chemical reaction between pollutants that have already been emitted called primary pollutants. The fact that ozone is a secondary pollutant means that it cannot be directly tracked as it is not directly emitted, which means that it is useful to have a model to forecast ozone and its correlations with other factors. So let's talk about the formation of ground ozone. The pollutants that react together to form ozone include nitrogen oxides and volatile organic compounds. These primary pollutants are emitted by human activities like factories, cars, the burning of fossil fuels, as well as organic chemicals and gasoline combustion. In short, these pollutants, with the addition of sunlight, together form ground ozone. This combination of factors is what caused us to hypothesize a correlation between these variables, which was why we thought it would be possible to use current pollutant and weather data to predict ozone levels. We chose Delhi, India as the focus of this project. India is one of the most polluted countries on Earth. In fact, out of the 50 most polluted countries in the world, more than half of the countries were in India. In 2019 alone, about 1.7 million deaths 18% of total deaths in India were attributed to air pollution. The visible effects of photochemical smog are also prominent in many cities, as you can see in this picture. Pollution is a problem that affects many people in Delhi. In Delhi, the air pollution was, on average, over 5 times the World Health Organization annual average standard. This has had severe health effects on the people of Delhi, causing significant increases in respiratory symptoms, including asthma, coughing, breathlessness, and chest discomfort. There was also an increase in the number of all-natural cause deaths in India, which correlated with the increase in outdoor air pollution, as well as an increase in emergency room visits for acute asthma, chronic obstructive airway disease, and acute coronary events. India also had freer access to data than other countries with severe air pollution like China, so it was chosen as the best country to analyze. So our research question was, can an effective Python machine learning model be developed to predict tropospheric ozone levels 24 hours in advance? The end goal of this project was to create a Python code which would clean up data and use machine learning to analyze relationships between current pollutant and meteorological variables and future ground ozone levels, using them to train a machine learning model that would be able to produce statistically significant predictions of hourly ozone levels in advance. This way, we could help improve on current methods of pollutant forecasting in the city by using methods that could eventually be applied to other cities worldwide. What this would mean is that it would allow people to be informed of the problem. Knowing about the problem and the dangers that it poses to themselves and others would give people an opportunity to alter their behaviors in such a way that lessens the severity of the issue. It could prevent them from putting their health at risk by unknowingly participating in high-risk behaviors at times when the ozone concentration is especially high. This way, people can avoid the adverse effects that come with this problem. It could prevent them from adding to the problem by doing things that emit more pollutants. For example, people could alter their plans so as to avoid activities such as unnecessary driving or outdoor exercise. As you can see, this would be especially useful for vulnerable populations, those who would be most likely to have serious health impacts. Basically, people would be able to limit their exposure to these pollutants and avoid contributing to the problem, thus reducing its impact.
All right, so now on to what we did for our project. As we mentioned earlier, we based our project in Delhi, India, which suffers air pollution due to factories, vehicles, lit garbage, power plants, and stubble burning specifically. These activities and more produce emissions of harmful gases, including carbon monoxide and nitrogen dioxide, which are both precursor chemicals of ozone formation, as well as hydrocarbons, particulate matter, and sulfur dioxide. One thing about this code is that it can be applied to other cities, as they also experience sunlight and these other primary pollutants that are necessary for ozone formation. And some examples of other high ozone cities that this code could be applied to include Los Angeles, Mexico City, Mumbai, and Beijing. For our materials, we used Jupyter Notebooks with Python 3 on a personal laptop. Some of the main libraries that we used were Pandas, sklearn, NumPy, and Matplotlib. The project consisted of about 4,400 lines of code in total, and the main files we were dealing with were comma-separated value or CSV files. So once we decided on the country of India, we downloaded a data set containing the daily pollutant measurements for over 25 different cities in order to first narrow down the scope of our project. So to do this, we created histograms of the daily pollutant levels for each city and each pollutant, and we added markers at the acceptable levels of pollutant. And we looked at how many cities had more days over the acceptable limits, and these were Amravati, Mumbai, Patna, and Delhi. We ultimately decided on Delhi due to its consistently high daily pollutant levels and the data's relative lack of nan, which are not a number or null values. For our pollution data, we downloaded a data set from the Central Pollution Control Board of India. This contained the hourly concentrations of over 16 pollutants over the course of about 5 years. We cleaned the data. So to do this, we created a code that checks each column in each row for nan or missing values. And if found, a nan value would be replaced by the average between the previous and next non-nan value. This process is called linear interpolation. And we did not fill in more than 3% of original values to ensure trueness of data. And this step was necessary for machine learning algorithms later on, which could not simply pass over a missing value. For our weather data, we use the Visual Crossing Weather Application Program interface to compile a data set of about 20 different variables, also of the hourly weather data for 5 years in Delhi, India. We repeated the cleaning process on this data, and we checked the distance between the pollutant and weather stations. We found it was about 4 to 5 kilometers apart, which we found acceptable. We then, once we had these clean data sets, we compiled the useful variables into one CSV file, which was then manipulated using Python. So on the bottom is a screenshot of the sort of raw data that we were working with. And this is an example of the clean data frame, which is the primary unit in the pandas library specifically. So before we could actually make a model, we had to do some pre-processing of the data. So this would let us explore the relationships between different variables in a variety of ways. So first we started out with just raw data exploration. On the left is a plot of ozone in blue and nitrogen dioxide, a precursor chemical, in orange. And as you can see, and they're just plotted over time. And as you can see, there is a strong relationship between the two. There's about a 5-hour time lag. And so then next on the right is a plot of the average ozone level over each day. So as you can see, it tends to rise during the day and fall during the night. And we also split them by season. So you can see ozone levels tended to be highest in the fall and lowest during the winter. Next, we decided to actually plot these relationships. So we started out by making scatter plots of ozone against the other variables we were considering for our model. We've highlighted the ones that are involved in the chemical reaction, but as you can see, some models or some relationships were stronger than others. Some were positive, some were negative. Some more analysis of this. The pollutants that were involved in the chemical equation of ozone showed significant correlations. Carbon monoxide's negative correlation with ozone indicates that it is a limiting factor in ozone formation, and nitrogen dioxide was positively correlated. And also just something to note about these relationships that we found is that they could be correlations or they could be actual causal relationships. So all we know is that they do tend to rise and fall together at least. And also some other noteworthy correlations were with particulate matter 10, sulfur dioxide, and temperature. Next, we moved on to looking at the correlations between not just individual variables in ozone, but all variables together. And this is important to analyze the relationships between each independent variable before even attempting any sort of regression. So to do this, we created a heat map to see potential issues. Issues can come up with multicollinearity, which is a problem that arises when, in some models, when the independent variables correlate strongly with one another. So this helped us look out for that problem in advance. So the way we decided to actually make predictions was with regression analysis, which finds the relationship between the independent variables and one dependent variable. So in this case, the independent or input variables were the current pollutant in meteorological data, and then the dependent variable or output was the ozone concentration in advance, since this is a forecast. And there are several ways to do this. This is a picture of the linear regression equation. It's basically the simplest form of regression. We tested a total of 7 different machine learning algorithms, including linear regression, k-nearest neighbors, support vector machine, random forest, decision tree, AdaBoost, and XGBoost. We also primarily relied on the R-squared value in order to evaluate performance. This is a metric that explains the proportion of variance in the dependent variable explained by the independent variables, and generally the higher the better. So first we had to actually decide on which hours specifically to forecast in advance. So to do this, we created new columns with the future ozone concentrations by making copies of the current ozone column and then shifting it down multiple times. And basically this allowed us to make predictive models for predictions from 1 to 24 hours in advance. And we use linear regression for this. And then we plotted the R-squared values. So what this let us see is the predictive ability of each model over time. So there is an expected decrease in predictive capability the further in advance, but there was something notable about the year-long model is that it tended to rise by the 24-hour mark. This could indicate some kind of more repeating cycle that happens every 24 hours that improves predictability in ozone. But we decided on this because it was about the same predictability as in 10 hours, but more than twice the amount of time in advance. So we decided on 24 hours. And something else to note about this is that we just tested out splitting the models and testing them by season, and they tended to have quite different performances. Next came feature selection. Now, this is not just done at one single point in the project. We were constantly refining and going over which variables that we were using, just depending on what step of the project we were on. But throughout the whole process, we used the significance level of 0.05, but the highest p-value we ended up working with was 0.00004. This means that there was a 99.996% chance or higher, at least, that the observed results are not simply errors due to chance. We also looked at the variance inflation factor of less than 10. However, this is only necessary for models that were impacted by multicollinearity. This is a histogram of the final variable correlations. So this is the correlation between current variables and ozone levels in 24 hours. So the strongest indicators were current ozone, nitrogen dioxide, sulfur dioxide, carbon monoxide, and so on. Next came the tuning, training, and testing of the models. So before we did this, most of the models had several different hyperparameters that can affect performance. So we used a code to try different combinations and return the best ones. And we also did some of this hypertuning manually. For the actual training and testing, we trained and tested using a 90-10 split. This means that 90% of the data was used for training the models and 10% was used for testing. And we also used cross-validation to get a fair evaluation of performance, which means that we repeated this 90-10 split a total of 10 times in order to test 100% of the data at some point, not just one small 10%. So for our model results, the best models were XGBoost, Random Forest, and K-nearest neighbors. Something else notable was that the model performance was not completely dependent on the computation time that they took. So XGBoost tended to be the best option because it had the highest score as well as the relatively lower time compared to Random Forest. And also K-nearest neighbors had an extremely low time. These are some scatter plots of the actual versus predicted ozone concentration. So basically, the closer to the red line, the more accurate the prediction. And not all of the models performed the same. Some did better than others. The best three, again, were K-nearest neighbors, Random Forest, and XGBoost. About 68% of the predictions had a percentage error of less than 25% for the best models. But after this, we asked, how could these predictions be improved? So we remembered earlier from our forecast time scores that the seasons tended to have a noticeably different predictive capability. So we did a bit more research and we found that India had 4 unique meteorological seasons that were different from the first split. So we refined them and made sure to include the 4-month-long monsoon and post-monsoon seasons. So again, we split the data by season across 5 years of data because first we had just trained across 1 entire year. So this time we split the data by season across 5 years and retrained each of the models 4 times. And overall, each of the models performed much better when trained by season separately than year. The maximum R-squared increased from about 0.61 of the year-long model to 0.75 of the winter model. They were able to predict the ozone concentration with less than a 10% error over 50% of the time. And they could also accurately predict the air quality index, which is essentially a danger ranking of ozone level over 92% of the time. And within one index, 98% of the time. We also created a ozone forecast calculator, which is an interactive interface that allows people to enter the current date and variables for an instant forecast of the ozone concentration in 24 hours and the air quality index as well.
Delhi, India suffered from 3 of the unhealthiest ozone levels for 270 hours each year due to an increasing amount of tropospheric ozone. The models were each developed to have an optimal performance, meaning that the models were not too complex, seen with the similar adjusted R-squared values and VIF values below 10. Our p-values were also extremely low, meaning that the results of this project were statistically significant. The winter model had the highest predictive power due to the fact that they had the lowest temperatures and the lowest precipitation levels from the entire year. On the other hand, monsoon season had the lowest predictive power, perhaps due to the frequent rainstorms that temporarily cleared the air of pollutants but reduced predictability. We faced several challenges and limitations during this project. For instance, the dataset we used did not provide enough information to make use of wind data, which could be helpful. Although ozone formation occurs as a result of solar radiation, our models relied on temperature due to the wider availability of the temperature data. The reason this is a limitation is because the results may have been better if we used reduced radiation rather than temperature. Our research improved on other studies in ozone prediction. For example, our studies used newer data from 2015 to 2020, while most other research was conducted in the late 90s to early 2000s. In our models, we used more input variables. We used 12, and other studies usually used 4 to 6 variables. Finally, we trained and tested more and newer machine learning algorithms using 7 methods, while other studies compared 2 to 3 methods. And finally, our best model had a higher R-squared value than previous studies, a significant achievement of the project. As for our future directions, the information and models learned in this project can be applied to virtually any city in the world, and there are many possible directions for real-life implementation of these models. Some of these possibilities include simple training and testing with data from other cities, using these predictions for government-issued health warnings, predicting other pollutants, further expansion of the models with additional variables, and more. Air pollution is a damaging problem which affects many people. It is our hope that with our project, we can help to combat this ever-increasing issue.
So as a review of what we did for our project, we cleaned and pre-processed hourly weather and pollutant data points for over 5 years in Delhi, India. We tuned, trained, and tested 7 different machine learning algorithms, each one trained on over 100,000 data points, first over the course of 1 year, then again across 5 years, split separately by season. The models were statistically significant, not overfitted or too complex, and the satisfactory prediction results indicate a great promise of machine learning in pollutant forecasting, especially with the seasonal models that have outperformed previous models made. And finally, this project served to highlight the different patterns and relationships that are essential to understand in order to regulate pollutants and better warn populations in the future. And thank you. So now is it time for questions?
Yes, it is. Thank you. Judges, questions?
Okay. I can start off. So you guys did a very lovely project, and I was curious for the division of labor for everybody.
Yes, so we'd meet over Google Meet several times a week, and we decided to divide the work by Alina was doing most of the coding and the details of the project, while Chela was responsible for researching the formation of ozone, and I helped with the slides and analysis of the project.
Okay, thank you.
I have a question. I'm looking at the code, like on the ozone forecast. I'm looking at XG boost. How do you decide on, learning rate and max depth. How do you pick those values?
Yeah, so what I did is I looked at different hyperparameters. Like I mentioned, there are different models that use different parameters. So I was just checking out different forums, and I found the kind of like best ones to test. So I would test different, I believe, I don't remember the specific parameters for XGBoost, but I used a code that would test different combinations. And I used this on a smaller data set because it would take hours to do it across the entire year. So yeah, I used that code, but I also had to do some tuning manually to just see which results would give me the best R-squared values primarily.
Okay, thanks.
Mhm.
You talked about adding wind. Have you considered adding information about the sources of various precursors on your maps?
Yeah, so this particular version of the models, it wasn't very like spatial, so we didn't take into account wind or different topography, but that could definitely be a future direction. Like I said, the data set that we use particularly, we couldn't really make use of that wind data just the way that we had it. But yeah, that would definitely be a big aspect since wind and just weather, and that's very spatial, can affect ozone and future ozone levels.
So this is Dave Janicki. When you're looking at the data sets and the results of your various models, have you thought much about where those models might need to be searched for improvements? I'm in particular interested always in, you're focusing on the regression sorts of models, but you've got these big envelopes of data, and I looked at slide 35, looked like it had some fall off at higher levels. And so, have you thought much about that? And certainly then, whether you have or not, thinking about those sorts of aspects where linear regressions may not be the answer, or there may actually be more information in the data than that first pass has allowed you to, is a good thing to go with. So I'd be interested in what you think and what you saw in your data.
Yeah, so when we were testing the different algorithms, it did seem to be like all of the nonlinear methods tended to do better than the linear regression model. I've kind of mentioned this, but this model can be expanded on. So depending on what data you have, you could add more variables, or it doesn't need to include every single variable that we had. It's very flexible, what I mean. So yeah, it kind of just depends on what you work with, but you can just retrain these models and our project basically on data from other cities, for example. So yeah, that's just something we considered.
Good, thank you.
Do we have any more questions?
Judges, any further questions?
I was going to ask, so could you talk a little bit about how you picked which machine learning algorithms to try for this project? So you had 7. How did you pick those?
Yeah, I kind of just read online about different regression models that were possible. There were more, but I tried to kind of limit it just so I wouldn't be testing a little too much. Or yeah, I just focused on the most popular ones out there. And yeah, we found that XGBoost, which is kind of like the newest algorithm, tended to do best.
Thank you.
Yeah, of course, thank you.
All right, ladies, thank you very much. Good luck.